So my name is Elvis. I'm from medical physics, and we do have a booth out there. And just in case you haven't had had the time to take a look at what we do in terms of the augmented reality, I do encourage you to pay us a visit during the coffee break. So together with Jonathan and David, I want to talk about our work, how to improve the efficacy and economics for certain procedures that are commonly performed in the IR suite. So here are our disclosures. So you may notice that we have a banner that it says WARP, that stands for Western Augmented Reality Program. It emerged from the vast lab that was led by Dr. Terry Peters over the last several years. But it was actually inspired by Dr. Narendra Paul's vision. That is, the central question we want to address is, where can 3D vision and augmented reality system assist the radiologist? So the way we envision this program to be carried out is in 3 stages. So at WARP 1, we want to target the student learners and patients, and to illustrate that high-resolution 3D display can improve the understanding of the anatomy and pathology. Moving towards intervention at WARP 2, well, we want to target interventional clinicians and trying to understand how interactive and integrated multimodality display can be used to add procedural planning. Finally, at WARP 3, in terms of the interventions, we want to be able to demonstrate that augmented reality systems can indeed improve the surgical outcome. So just to give you a very quick overview of what is it that we do, we carry out this WARP program in forms of image-guided intervention. That is, we combine advanced imaging, image processing, surgical metrology, how to track surgical instruments in 3D space, and implement this augmented reality system to guide or to assist the surgeons to perform, in this case, the needle guidance. So what you see in this video is that we have a track ultrasound, and we also have a track needle. And what we do is we are displaying that 2-dimensional ultrasound in its correct 3-dimensional space. And we also do an overlay on the needle itself, so that when you're inserting the needle, you can see where that needle is, even if it's inside the patient. And you can see from this video that we have the ability to do this in basically sub-millimeter accuracy. So in other words, what we do is a GPS for surgery. The way we do it is that we have a way to track surgical instruments and patients using some form of tracking system that could be surgical robotics, optical tracking system, or magnetic tracking system. And through that tracking system or surgical metrology, we have a way to register preoperative image modality with intraoperative image modality and provide you with image fusion. Once with that image fusing, then we move all that information into advanced 3D display and provide 3D visualization to the surgeons. So I'm preaching to the choir here, but let's talk about why we want to do this. So let's using the spine needle as an example, right? So when we want to put a needle into either epidural procedures or pain management, what the student learner has to do so far is that they have to couple with someone who is more experienced, learn how to operate and position the C-arm, get the image that we're looking for, understand that image, and basically look for that Scotty dog image in order to say, this is how I want this C-arm to be. Right, so it takes a lot of time, takes a lot of experience, and from what I heard is the residents basically had to go into the IR of the hour in order to get that opportunity to use the C-arm. So at WARP 1B, what we did with one of my students is that we leverage the 3D printing technology, and we manufacture a physical C-arm in 10:1 scale. And we track it using wireless and battery-powered accelerometers, and we register a real patient CT into that simulated 10:1 table. And based on and this device is entirely wireless, body power, and talks to your computer using a Bluetooth protocol. And by physically manipulating the C-arm, we can generate, based on the patient CT, a simulated X-ray so that the student learner can begin to understand that if you want to get a certain image, this is how you should position the C-arm. And this system costs about $150 Canadian, adjusted for the inflation. And of course, we're not satisfied there. We take that kinematics and the math that we developed, and we move it towards into a virtual reality environment. So what you see in the bottom left of the image is my student wearing this head-mounted goggle that all he sees is this video that you see in the middle. And what he sees is a 1-to-1 scale virtual C-arm with the standard reference image showing the background. And through the control using the game controller, whenever he or she is moving the C-arm, what you will see is that on the left of that screen, the one that's standalone, that image will be updating in real time, right? So the learning objective then is, again, trying to understand the position of C-arm and try to match the dynamic simulated X-ray to match with one of these standard image that we're seeing. So that's a work one project. Now moving towards the clinical translation, a work two project that I've been working on is actually how to utilize this virtual reality environment, not only for virtual consultation, but also for anatomical measurements. So what you see here is a four-dimensional TE ultrasound that imaged the whole heart. And in collaboration with the King's College London, we have the ability to not only for one user to visualize this 4D data in this VR environment, we can actually have another person, and in this case, transatlantic, to visualize the same virtual environment as the person in London, both London actually, and then begin this virtual consultation. So if you have questions about what is it that we're looking at, and which area we should pay attention to, you can get an expert that doesn't even have to be physical in the same location. And what we found out is that in the VR environment, because we had the ability to place basically a slice, this red 2D bounding box through that three-dimensional ultrasound volume at any oblique angle, we can position that slice at the angle that, for example, image the entire length of the chordae, so that you can get a much more accurate and anatomical measurement of the chordal length. Another work two project that we've been working on, this is one of the demos we have outside. The initial application is for patient education. So I've heard all the story about, some of the elderly patients when they want to, when the surgeon want to get a consent to do certain procedures, the surgeon will have to explain a very complex surgical scenario and anatomy to the patient. And the question that always wonders, that we are wondering is, are the patient really indeed informed, right? So in this work two project, what we do is to leverage augmented reality system, and we have the ability to allow both the surgeon and the patient wearing two different augmented reality head-mounted display to visualize the patient's specific anatomy. So in this scenario, we can say, okay, here is your brain that we get from your MRI scan or CT scan. Here is your aneurysm, and here is how we are going to treat it, right? And we have the ability to manipulate the 3D model interactively, view it from different angle, augment it with a video, voiceover, etc., etc. And going back to biopsy needle guidance, because we have the ability to track both the ultrasound and the needle in a very precise manner, a Warp 2 project that we have been working on for the last couple of years is actually for liver ablation. So what you see in this video is that we manufacture a liver tumor that we actually have it with us in our booth. And we have the ability to track the needle and overlay what we think the ablation zone would be. So in going back to the analogy of GPS for surgery, the objective of this needle guidance or liver ablation now is to simply overlay that spherical ball that represents what the ablation zone would be to the entirety of the tumor. And we're hoping to move in towards a clinical application anytime now.
Awesome. So Elvis did a great job, but it's really important to note that him and Terry's lab really, I was invited there about a year and a half and just blown away by all the stuff they're doing. So it's kind of endless when every time you go over there doing something new and some new piece of technology sitting around. So, but like I said, about a year and a half ago, I was invited over there with Dr. Hocking, and we saw them working with the HoloLens. So essentially what I'm here to talk to you guys about today is some of the novel programming done by Dr. Hocking to kind of develop the HoloLens 2 for an angio-specific application. So people have been working with the HoloLens in multiple different applications, primarily dealing with 3D volumes and trying to overlay them over top of the live patient. You know, doing some digging into this, we had a lot of discussion. As much as it looks really cool, we really felt like that type of registration, working with registration in the angio suite, knowing that the accuracy is always a challenge. We thought it was a great show, but not really clinically relevant in any way. So we set off on a path to try to develop kind of a novel program that would capture the angio outputs and display it in real time on the HoloLens. So we chose the HoloLens. There's multiple heads-up displays available, but the HoloLens has a transparent lens. So essentially, working in a healthcare setting, having the connection between the doctor or the tech or the nurse and their patient is an important thing to have. So not looking at a digital screen, but yet seeing the physical world and augmenting that with digital aids, we see as like a good avenue into it. So a little bit of an overview of what we have so far is essentially we've developed a plug-and-play piece of technology that connects directly with our angio system. As you guys saw in the demo out there, it also connects with ultrasound, connect with the CT system, and gives us live streaming at very high resolution, low latency. And it allows us to, in a sense, place a digital screen anywhere we want. You can see in that lower picture there, that's an area of the room that equipment couldn't normally place the display. So gives us the ability to change the size and position, and we're just starting to slowly implement features. One key one we knew early on that we wanted to be able to lock it because accidental interaction was a big problem. As you start to pinch a needle or move a finger control syringe, the system would react. So, you know, and the big question is why. So, I mean, the technology is cool and it's a lot of fun to work with, but really, we wanted to make sure we answered the first questions. Why will we even bother in doing this? So anybody who works in our new angio suites knows that those large screen displays are very heavy. One of the very first complaints we had when we installed our new room was from our anesthesia colleagues, where we put this giant wall between them and us, and they felt really disconnected from the patient and the rest of the team. Not to mention that that large screen display has a lot of collision risk with the imaging equipment. We're all packed into a tight space. And it takes up about 50% of the most crucial area, which is that table side. So when you're trying to work on a procedure and half of the access is taken away by this large screen display, we thought that was a really good reason why we wanted a better solution. So, but one good thing that those large screen displays kind of brought to the angio suites is the ability to view multiple screens. So currently in an angio procedure, we'll have 1 or 2 live fluoroscopy screens. We'll have multiple references, our ultrasound images, patient monitoring, previous imaging, and the cone beam CT that I kind of showed earlier, all on one screen. Our radiologists typically only want to see what's relative to them at the time. Our nurses want to be able to see the vitals, maybe even the allergies or the power chart. And the techs really want to be able to position the equipment without needing to obstruct anyone's view. So one key benefit of using a HoloLens would be we can all have an individualized screen in a shared environment. So we see that as a big value. And you know, back to the ergonomic challenges, not just for the techs moving the screen around, but the sterile field itself. So our ceiling heights in the angio rooms are not always that high, so having to lift the equipment up and over a sterile field isn't the greatest aseptic technique. So really kind of trying to give solutions to those problems. And then one key thing that isn't always discussed is the visual and motor field disparity. I know we watch our rads do these procedures all day long, and they don't really complain much, but they tend to work in one direction and have their head kind of turn to the other. So we try and get our equipment as close to them. A lot of times the ultrasound's on the other side of the table, or there's auxiliary equipment in there. So they end up having to kind of turn their head sharply and I guess kind of understand how their hands are moving in relation to a screen that might be 5 feet away. So the visual motor field discrepancy was evaluated by Daniel Allen here and his team. So they did a feasibility study last year, kind of assessing this. They had novice users kind of do ultrasound procedures with and without the HoloLens. And on a 5-point Likert scale, they had an average of 4 or 5 where they agreed or strongly agreed that the HoloLens was superior and showed kind of modest accuracy improvements. So it was a good example of a non-inferiority study. There was also a large study that was referenced in there with 75 intermediate and advanced users, and 95% of the users agreed that the HoloLens or the heads-up display added a benefit to their procedure. So Elvis had kind of shown a little bit earlier. Obviously, what was really important to us is that we developed an application that we would be able to use clinically ourselves. So 3D volume rendering poses significant challenges as far as time and resource on the GPU and CPUs. So working with the students there to kind of use the HoloLens to develop a patient education tool. So our neuro IR patients receive that rotational imaging that you guys saw, which gives us already segmented images. So working with the scientists and doing some background knowledge, like figuring out how to take medical imaging and turn them into 3D volumes to display in a HoloLens was one step. And then working with the students to develop a patient education tool in a hope that one day we can kind of implement that 3D rendering technology with our live streaming technology and be able to offer everything that the large screen can offer. So from a hardware perspective, very small PC, you wouldn't even notice it, integrates directly into our Artis Icono. We've created this to be vendor agnostic, so it can plug and play into any system, and we have direct fiber optic connections. One thing that's really nice about the angio system is the cockpit allows us to control additional computers. So from a user's perspective, you're going to use the same mouse and keyboard you use to operate your angio system, and you're going to be able to operate the HoloLens application. But one key important feature, I made these slides about a week ago, and then I went away for a week and I came back. And so our current render train is now our past render train. So one thing that a lot of people have tried to do when deploying this technology is use something called holographic remoting. So to simplify it, it's essentially using 1 or 2 computers that handle all the source imaging and then project kind of a almost finalized image to the HoloLens. This can create quite a bit of latency, also can have quite a bit of challenge as far as being close to the system, and just needs a more robust computer to do so. So it's kind of already progressed to what I was going to call our target render train, which is a host computer that simply just grabs the information. So a very simple Windows-based PC that you plug into a machine, kind of packages the information, and then transmit it through a server. The HoloLens themselves receive that information and then communicate with each other. So if you have multiple people wearing the HoloLens, they're communicating with each other to create a shared environment. So if I was to take an object and place it in a position, you would be able to see it in that exact same position. So and it also really significantly reduced our latency. And then so that brings us to our first experience. So of course we haven't used this clinically on any patients, but we hopefully to do so soon. But most people who have put this on have been very excited with the technology. And it's been really fun to see everybody. I don't know how many have made it out to the demo so far, but it's pretty cool to see. And you're going to see when we start implementing it, a lot of people kind of poking into the air and moving objects around that you can't see, which does startle a few people. But rest assured, they are looking at images, and we're hoping with some RAP, we're going to get to it soon. So I know we showed some of this last year. So important differences. When we first started on this, kind of a project, we were using third-party applications. So essentially taking multiple different pieces of software and just connecting them together. So it sounds easy, but it's still quite a bit of work to that. We went back to the beginning, and Dr. Hocking essentially started from the ground up and programmed the application from scratch. So there's no third-party applications involved. It's essentially completely controlled and owned by us. So that gives us scalability, customization. We can kind of build on this as new needs come along. So, just a little overview of what we have. So we have a very low latency, high resolution live image stream. It is able to track your position, so it keeps your gaze wherever you're standing and looking at the screen. Single user interface, so we can have as many users looking at the screen as possible, but they're all looking at the same thing. And then we've implemented that screen lock thing. So moving forward, obviously we want multiple different sources, so we can display different things on each HoloLens, create a much more user-friendly user interface, and increase the customization, and obviously incorporate those 3D images and previous PAX images. So I see a really good opportunity for a lot of other people to become involved in using AR and connecting with robots on various projects. So we're going to start to do an REB shortly. And once we have REB, because it deploys to a HoloLens, we can have multiple different studies going on, people trying to apply this application in different ways. And with Dr. Hocking continuously kind of implementing new upgrades to the program, we can then kind of share that with all the different deployed HoloLens. So, and of course, we showed patient education and a little bit about remote proctoring. So, kind of hoping to explore that option as well. Thank you.
I didn't prepare any part of this because it was a short presentation and we were already going through 3 different people. So I just spent my time doing the programming to get this ready for today.